right. Welcome, everyone. My name is Alexandre Stepanovic, founder of Cascades Analytics, a media and advisory platform focused on the psychedelics and neuroplastogens pipeline. We go where the action is, speaking with the founders, scientists, and regulators shaping the next wave of psychiatric drugs. Joining me today is Dr. Jason Wallach. Jason is assistant professor at St. Joseph's University. He started a partnership with Compass Pathways to develop novel psychedelic drugs as therapeutics. Jason and his lab, in partnership with John McCorvey and Adam Halberstadt, published in 2023 a key paper characterizing the serotonin 5-HT2A receptor intracellular signaling cascades mediating the head twitch response, a proxy for a psychedelic effect. Jason, thank you so much for being here today. How are you doing?
Great. Yeah, thank you for having me, Alex.
Yes, let's dive right in. So why don't you summarize the findings of the Nature Communication article I mentioned, published 3 years ago now, which is quite a seminal paper.
Yeah, thanks. So I mean, there was quite a few different things we were kind of hoping to achieve, but when we started out, we were interested in building tool molecules that could sort of distinguish between the different intracellular signaling pathways that serotonin 2A receptors can initiate. The sort of two classic classes are the G proteins and the arrestins, beta-arrestins. And yeah, I mean, essentially a lot of work. We ended up finding several compounds through SAR optimization that and some structure-guided informed approaches that ended up showing good bias in these assays we were using with respect to not activating the G protein pathway and able to cause the arrestin recruitment signal. And what's notable about that is existing psychedelics, as we found and many others have reported, don't show any differentiation. And that compounds that are able to differentiate are called biased. So existing psychedelics are not biased. They cause G protein activation, more or less similar activation of the arrestin pathways. And so these compounds were unique in that they can signal through one and not the other. The other thing that I think was valuable in our tool compounds was not only did we have compounds that seemed to have a good degree of separation in their ability to activate arrestin and did not activate the G protein pathways, there were also compounds that spanned the range of efficacy for activating those pathways, particularly the G protein, GQ pathway. And what this means is, drugs can sort of bind to a receptor, but that doesn't tell you anything about what they do to the receptor. And efficacy is essentially like how strongly do they activate the receptor. Normally, you normalize the signal, the magnitude of the activation, to a reference compound of serotonin, for example. So serotonin gets set to 100%. It's the endogenous neurotransmitter. It's called a full agonist. And so these other compounds, some would activate 100%, 105%, 90%, 80%, 60%, 40%, 30% of serotonin. And we were able to use those compounds as well as the biased compounds to sort of establish that the head twitch response in mice, which is predictive of psychedelic effects in humans, was associated with the G protein pathway. The arrestin biased compounds did not show any head twitch response. And to show that that wasn't just because they were shitty drugs, right? They actually do get into the brain. We show that they block the head twitch from a known psychedelic like DOI. So they're getting into the brain, they're binding to that receptor. They just don't activate it in the way that psychedelics do, which our argument is through these G protein pathways. That's kind of, I guess, the summary of it. There's a lot of little nuanced bits we could follow up on, but.
And what about at the level of the receptor itself, and how those different cascades are activated?
Yeah, and actually, I
Arrestin
guess I should.
versus GQ.
Yeah, and actually, I realized I probably, because I went into the head twitch bit, but the real utility of this finding is that you can use the GQ efficacy as a predictor for whether a given 2A agonist will be psychedelic or not in humans. Essentially, we found a threshold where compounds above that threshold will cause the head twitch, and humans perceive them as psychedelics. We tested 30 psychedelics, and all of them were above that threshold. And not only that, the number of times the mice twitch their heads like this correlates with the efficacy to activate the receptor. If you activate it 100% relative to serotonin, they twitch more times than if you activate it 70%. And so that's useful because now you can use an in vitro cell-based readout to design compounds that have different efficacies, and you can predict what they will do in head twitch and then ultimately humans. I think it is highly predictive of humans. We tested a series of non-hallucinogenic or non-psychedelic 2A agonists, and all of them are below that threshold, as you would expect. Now, humans will take these compounds and say they're not psychedelic. They're just different. It's not to say they don't have acute psychoactive effects. You can feel a little altered, stoned, especially as you get closer and closer to that 70% threshold. So, it's not quite black and white. The mice show a very clear head twitch or not. Like if you cross that threshold, I mean, we had compounds really close on either side, and it was highly, highly yes or no. But in reality, I think in humans, there's a bit of nuance there. And then things like polypharmacology, right? Other receptors complicated even further.
Mm-hmm. Mm-hmm.
So I just wanted to make that point because that's sort of the application of what we did.
Right. And why is that 70%, you think? Is there like a stoichiometry or is...
Well, whatever psychedelics are doing in humans for the neurons to be affected by 2A to the extent that cause psychedelic effects, that 70% is what needs to be achieved. Now,
The threshold.
I want to be clear that if I measure these compounds in 6 different assays, that 70% number might change. And even if I measure it in different neurons, like this neuron might respond to this 70% as 60%, and this population neuron 40% or 30. What matters is the rank order of compounds. Like this one is lower than this one, which is lower than this one. That is highly conserved across assays with some technical caveats, as long as your assays are well designed to distinguish what we call partial agonism. But the rank order is what matters. So 70 people use that number a lot, and it makes sense in our assays that we ran that was 70%. But it would be possible to change that number. But again, you would just shift that down. Then it's 50% in your assay. So you have to benchmark your assays if you're trying to use this strategy. I think it's highly predictive, but you have to benchmark and make sure you're able in your assay to distinguish the non-hallucinogenic, non-psychedelic 2A agonists from the full, and ideally have a range of compounds. So 70% is not a kind of magic number as much as it's predictive in that assay of the level of activation you need in humans to have a psychedelic effect.
Mm-hmm. And it's reported, it's normalized to serotonin in your essay.
Correct.
Where you, you knew this already, that serotonin was a non-balanced agonist. It activates the arrestin and the GQ pathways to the same extent.
Yeah, and that's another interesting thing, because by definition, it's going to be the same percent, right? Because you normalize the serotonin in both assays. So 100%, whatever serotonin does in arrestin is set to 100%. Whatever it does in GQ is set to 100%. So that's something to keep in mind too, is it doesn't mean like the same number of arrestins, of course, get activated as the G proteins. It's just you have to normalize to another reference molecule. And serotonin makes the most sense because it's the endogenous neurotransmitter, right? Like it's intuitive that that's a good one to select. Depending what you're doing, sometimes people pick a different reference. That's fine. It just shifts everything.
And so if we start at the receptor, in your article, you identify an amino acid that is responsible for, the toggle switch that triggers the dissociation with the alpha subunit of the GQ protein, if I'm correct. So but not all agonists, not GQ dissociation. How am I going to put this? The amino acid responsible in the receptor for the GQ activation might not be the same as for the arrestin activation, or it might be the same, but it's not the same conformation. Could you elaborate on that?
Yeah, what we found through SAR and modeling, docking, molecular dynamics simulations, and then also mutagenesis was that there was a key amino acid residue, the tryptophan 336, and this is a highly conserved residue across many different G protein coupled receptors, particularly monoaminergic, dopamine, norepinephrine, etc., GPCRs, class A GPCRs. And so it's long been known that it is important in activation. That's why it's called the toggle switch. Many different molecules, ligands will modulate it by their interaction. So a lot of antagonists, for example, if you look at their structures, the bound antagonists in the protein structure on the protein data bank, for example, you'll see that they block that tryptophan from being able to sort of rotate. And so they come in and act as like a wedge, and this door, or whatever you want to call it, can't swing down. And this swinging down initiates a conformational cascade. There's other things that do this too, but initiate this conformational cascade that changes the shape, the conformation of the receptor, shifting it from inactive to active, for example. And so what we found was that these N-benzyl phenethylamines were sort of well positioned to interact with that toggle switch. They're also close to TM7, which we were very interested in. That's also been known to ligand's ability to modulate TM7 can influence bias as well. But yeah, I mean, so essentially what it appeared was that this is our hypothesis, that these bias compounds will interact with that toggle switch residue in a different way. We're putting bulk there, and they push on it and kind of stabilize it in this intermediate state where you don't get G protein activation, but you still get arrestin recruitment. You kind of trick the receptor into it, or it's almost like you're tricking the cell into thinking the receptor's activated with respect to arrestin, but you didn't actually activate it with respect to the G protein. Like normally you get a G protein signal, and the reason they're called arrestins is because they arrest that signal. They come in after and shut it down. They're like a mechanism for regulating the extent of the activation. And so you're tricking the receptor is sort of in this kind of active, kind of not state. So it's not activated enough to initiate the G protein activation, but arrestin's like, oh, I'm good, I can fit in here, and it binds, and you get arrestin recruitment.
Isn't beta-arrestin recruitment a basal phenomenon?
Yeah, most GPCRs are going to interact with arrestins. Now, as I said, like one of their major functions is inactivation of the receptor, as well as then internalization. Often the receptors are internalized with arrestin bound, and it plays a key role in that internalization process. That said, arrestins also will interact with other proteins when they're bound to GPCRs and initiate their own intracellular signaling cascade. So they're doing a lot. They're not just inactivating and internalizing, they're also stimulating this intracellular signal. And what's interesting, there's some data with some GPCRs that once they're internalized in these endosomes, they continue to signal with arrestin bound, which, makes sense, right? There's information to be gleaned from the cell's perspective about what has happened.
But now at a much less at a fixed occupancy.
Occupancy's tough to try to relate. So especially
In
with
the
GPCRs.
yeah, sorry, go ahead.
Like what's interesting about that is that, so the potency of an agonist for a GPCR in a functional assay does not correlate. It depends to some extent on occupancy and the binding affinity, but what's complex is that efficacy also modulates it. So to predict in vitro functional potencies for GPCRs, you would need to know the binding affinity, but also the efficacy, because that's going to shift the potency. And so you could have two different drugs like psilocin and LSD, where the same level of signal is at different occupancies. LSD would very likely do this at a lower occupancy than psilocin.
But in the endocytosome, it's not an open synaptic cleft anymore. So the concentration of a ligand is fixed.
Yeah, that's a great question. So, and that gets really complicated, right? Because generally you would think the ligand is going to be bound still to the active receptor with arrestin. It gets internalized. So then it's like concentrated in the endosome. The extent to which ligands can come on and off in that state is very difficult to actually measure and investigate. People have tried, and there's some evidence they can come off, and presumably, especially for recycling, they need to, right? So the cell might have mechanisms, the pH, etc., to sort of kick it off. Again, how long arrestin stays bound, though, it gets complicated. So that's not clear that then arrestin immediately dissociates.
And then there's phosphorylation involved and things like that. But okay, so now we have an understanding of biased agonism and partial agonism, and they are actually two independent properties of ligands. We can have full agonists that are biased. We can have partial agonists that are biased, and everything in between. Now we have a biased agonist hitting the 5-HT2A, activating GQ, not in the same way as it activates beta-arrestin. What happens downstream? Do both cascades lead to plasticity, and which form of plasticity? And are both of these forms necessary for therapeutic benefits?
That's the billion-dollar question. It's a great question. So one thing I'll point out is we personally didn't find G protein biased compounds that don't cause any arrestin. And although people appear in some assays to have found those, I am sometimes worried about the assays that are being used. Again, this gets kind of technical, but I think you have to be very careful about that. I mean, it seems reasonable that it's possible. That said, we didn't see any indication of that, and it seems quite tricky, because when you have activation, you're going to often lead to some arrestin recruitment. But again,
it's not symmetrical.
It's not symmetrical.
Probably always have a beta-arrestin activity.
But I think it's hard to get the G protein activity and not get arrestin, because it doesn't just depend on the drug anymore. It also then the receptor gets phosphorylated and it can get inactivated that way. And so it's kind of nuanced, and we don't know yet. So I just wanted to point that out. That's something we really are looking for and trying to do, but it has been extremely challenging, I'll say. Now, as to your question of synaptogenesis and this psychoplastogen effect, this is the issue with that is, like, every psychoactive drug is capable of inducing psychoplastogen effects. I'm not aware of one that's been looked at where in some measurement, they don't cause that effect. And this is because this is what neurons do, right? If you fiddle with the receptors, you're going to change their, either if they're developmental neurons, their kind of growth patterns and neuritogenesis. And also, if you stimulate these receptors on neurons, you're going to change their connectivity with other neurons. And then that's going to lead to connectivity changes elsewhere in the system. And that's not to say these effects aren't important for what psychedelics are doing, but I'm skeptical of treating it as some kind of broad mechanism that, oh, psychedelics are specific in causing this psychoplastogen effect. And, we could go into this in some detail, but this is not a new idea. People have been trying this for decades in depression. A number of drugs, including in the NMDA receptor antagonist space and elsewhere, looked amazing in these psychoplastogen models in vivo in mice and rats. They caused robust, spine density increases, whatever you wanted to measure. But then in the human phase 2 or phase 3 trials, they failed miserably. So I'm skeptical that those readouts are predictive of what's going to happen in humans. I'll give you another example. You can induce plasticity changes with 2A antagonists in some assays, including in vivo. Now there's differences. You have to typically give them multiple times, but still you could get the same effects. And I don't mean the same, like maybe you find a difference in the shape of the spine or the neuron, there's nuance, but I get concerned when it's like we sort of treat them as, oh, they just like increase connectivity and that restores this imbalance in depression and everything's fixed. I think it's a lot more nuanced and complicated than that. Cocaine causes similar effects. Nicotine causes similar effects. Right? These aren't rapid acting antidepressants. If your readouts are predictive, they would be. And same thing with R-ketamine. That was one of the NMDA receptor antagonists I mentioned, right?
Right.
All of the in vitro data suggested R-ketamine would be the antidepressant, an enantiomer in ketamine, and it does not appear to be. It's the S. And there's another NMDA receptor antagonist, Repastinel. Same story, and billions of dollars, not, well, $500 million at least, were spent, hundreds of millions on the development of that compound. It looked amazing in all these preclinical psychoplastogen assays. And then in humans, there was nothing. So I guess my point is, like, I'm sure I could give someone our different compounds, different labs, and depending how they did the experiments, I'm sure any possible result with synaptogenesis or neuritogenesis could come back, because it's such a non-specific thing. If you fiddle with neurons, you get this effect. It depends on timing, dosing, frequency, temperature, the serum you're using. It's just complex. And I don't want to say that we shouldn't be pursuing it. I think it's very interesting. But I think we should be very cautious. We should learn from the failures of the past several decades in the depression literature, and be cautious and try to figure out how are they doing it in a unique way that is truly predictive. The problem there is any psychoactive drug will cause unique effects in this way, right? They're all going to be a little different. So you're like searching for a needle in a haystack, like which one of the trillion synaptic changes in the brain is predictive of the therapeutic effect. Good luck,
How can we assess the responsibility or the involvement of each cascade, arrestin versus GQ, in therapeutic effect?
Well, right. So I think one of the things we were excited about with these compounds is they can serve as tools for allowing that to be done, or at least that people could replicate our strategy and do it with their own molecules, right? So now we have a way of, in the past, people just said, this compound's non-psychedelic because it's inactive in head twitch, but they didn't have any idea, whether that's because it's a partial agonist, it's biased, like the profile was sort of hazy, like it just is non-psychedelic. There were a lot of different ideas about why. If we have a good understanding of, at least a reasonably predictive understanding of why, our model is predictive of hallucinogenic effects in humans. And we understand at least like relatively what these compounds are doing in these different pathways. And you really do need to translate to in vivo models, though, to do this right, preclinical in vivo models. But then when you test these drugs, as long as you do the trials well, I think we're going to get very informative data back about, what level of activation do you need for this indication? Do you want a biased profile here? Do you want a more robust G protein activation? For example, we saw with the biased compounds, which I think is especially interesting, these arrestin biased compounds, in some ways they behave like psychedelics in behavioral models. In other ways, they behave like inverse agonists, antagonists, like antipsychotics. And that's really interesting. So,
excuse me, what models are you referring to?
So the antagonist behavior was the ability to block PCP, phencyclidine induced hyperlocomotion. You give mice PCP, rats, they run around like crazy. 2A antagonists have long been known to attenuate that locomotor stimulation. So our bias compound, the 2,5-N N1 NAP, blocked, right, attenuated that PCP-induced hyperlocomotion. The other common model used for 2A antagonists in vivo is for antagonists is the ability to block head twitch. And so they also block head twitch, right, as I said earlier. Now, where they act like psychedelics is really neat, and we predicted they would do this, right? If they're stimulating arrestin in vivo, what should they do? They should internalize the receptors. In other words, that process is implicated in tolerance to drugs. So by stimulating arrestin, you get internalization, and eventually, basically, the receptor thinks there's so much activation of 2A happening, I don't need to make as many receptors anymore. And so you get a decrease in receptor. And what happens if you give DOI 5 days in a row to mice, on the 5th day, they have a very weak head twitch response, if at all. Same with humans, right? You take LSD 5 days in a row, that 5th day, you're not really going to feel much. And so
desensitization, yeah.
Yeah, exactly. And so we predicted, okay, this naphthol compound, if it is signaling through arrestin, it should induce tolerance, right? Basically, you give it for 5 days, and then you should, when you give a mouse a psychedelic, the head twitch response should be attenuated, as if you gave them a psychedelic for 5 days. And that is, in fact, what happened. And to sort of test that this is unique, we also did it with pimavanserin, an antagonist, and that did not cause this effect. It failed to block, failed to attenuate the head twitch, as you would expect. And there was actually a slightly higher. I don't think we tested it for significance, and we certainly didn't power the study to, suggesting possibly upregulation of the receptors. So these arrestin bias compounds are interesting, right? Because you think about what you're doing here. You're tricking the cells into thinking they were activated with the G protein response, but they weren't. And so they respond as if they were activated with respect to the arrestin signal. So anything that arrestin could mediate therapeutically could be valuable, but also anything that blocking 2A could be useful therapeutically could be valuable with these compounds, because they're able to block 2A G protein activation, but cause a different arrestin response than the existing inverse agonist antagonists, which don't cause any arrestin recruitment.
Are you looking ideally for a compound that is not recruiting GQ to above 70%? So, but enough to activate both cascades, arrestin and GQ?
Yes. So a lot of the partial agonists in the GQ pathway give an arrestin response. What's interesting is the amount of arrestin varies between, like tryptamines, they tend to track pretty well. Like you get a little bit higher or lower arrestin, but nothing major. Whereas some of these N-benzylphenethylamines, there can be a big discrepancy in the arrestin recruitment versus the G protein activation. So to kind of answer your question, yeah, there's some nuance there of like, what is the best GQ arrestin profile for partial agonists? We don't know that yet. I mean, there's so many interesting follow-ups with this work, and I'm interested in all of it, you know, and from a tool compound perspective, we're always looking for anything we can find or make that will differentiate. You know, I love serendipity. I mean, we do use structure-based design and targeted approaches, but I'm big on, you know, playing, exploring, and let nature kind of guide you, you know, and a lot of cool, exciting things come about. So.
But isn't there a plasticity associated to beta-arrestin and a plasticity associated to GQ pathway?
Absolutely, everything. I mean, there's not plasticity, there's not a pathway in a neuron I think you could target that couldn't somehow affect the plasticity. So yes, but what does that really mean?
And how to measure it?
Yeah, and you know, again, like the rodent models for depression are terrible for predicting outcomes in humans. There's no successful track record at all. Every first-in-class antidepressant was basically discovered by serendipitous observation. Clinical. Someone said, oh, these people look happier. Or reasoning with like postpartum depression that there's a hormonal imbalance. And so all of it can be traced to human data. Anytime we've had a new mechanism and tried it in mice and we said, oh my God, it's making them swim more in the forced swim test. And that compound went to phase 2 or 3 trials, it failed. And there's tens, if not hundreds of compounds like that. You know, so at some point, the models we're using are flawed, right? Like if there's so many false positives, why are we still using those? I don't think they have any predictive validity for depression. The forced swim test and tail suspension. I do think there are ways to sort of move forward. There's essentially like an RDoc approach. NIMH came out with this, and it's been a little while since I've like really looked at it closely, but I like the idea, the concept, which is instead of these like global disease models where it's just like, oh, the mouse swims and that predicts an antidepressant response. You use models that are predictive of specific deficits in humans that are seen in the disease state that presumably have shared overlapping physiology in the rodents, right? Like hedonic response, memory, motivation, attention. Right? These are things that are more likely to translate. Now, there's still, again, can be major differences. And there you take a broader approach and you say, okay, what are the actual deficits in this, you know, disorder? And, you know, what are some models we can use that could get at identifying molecules that could improve those deficits in humans? And the RDoc approach wants to even move away from the DSM diagnoses, right? It says like that's flawed too, because you're grouping all these people together who are heterogeneous. We know 2 people with depression can have completely opposite signs and symptoms. I mean, except for maybe like, you know, feeling low mood, whatever exactly that means. But, you know, one person can be sleeping all the time, have no motivation, feel very sluggish, is eating a lot. Someone else could be, they can't sleep, they're not eating at all, they're really agitated. Do those people have the same underlying physiological imbalance? Like maybe, but why would we assume that? We've looked for decades, we've not found a biomarker that predicts major depressive disorder, treatment-resistant depression. We have no clear hypothesis of, oh, it's an imbalance in this system. Everything like that with further probing has fallen apart, right? So maybe the issue is that it's not that we can't find it, it's that it doesn't exist because you're not looking at a single thing. You're lumping together tens, 100 different disorders into one blanket thing that a questionnaire is supposed to capture improvement in, right? And so I like that idea a lot of moving away from that. Like, what is this person suffering from, right? What is the problem in that patient? And can we develop drugs that improve those core deficits? I think that's far easier from a drug development standpoint than improving scores on the MADRS rating scale, like in a heterogeneous population of people. So I blame the psychiatrist, not the medicinal chemist.
Right. But looking at, the indications a little bit closely, you see that demoralization and depression are not exactly the same state, and depression might be more of a vegetative, vegetative impairment, whereas demoralization is more of a severance from your future self. Somehow you can't project anymore, and you can be depressed but not demoralized, and you can be demoralized but not depressed. But it looks like after the, you look at the work of Ross and his team at NYU, that psilocybin actually really improved demoralization much better, and that might be the indication instead of depression. So 5-HT2A might be a good entry to understanding that demoralization may be better than depression, or maybe even another indication that we don't know. I mean, it's just a continuous adjustment to what we can grasp.
Yeah. And look, I mean, even, two different psychiatrists will disagree about the diagnosis, especially if they're in isolation.
Mm-hmm.
I mean, and the DSM, they push this biological psychiatry, and I think there's value in what we do, with psychiatry. I'm not like anti-psychiatry. I don't want to give that impression at all. But, there really isn't a biological foundation at the moment. Unfortunately, it's just the reality. And so people are doing the best they can. But the point I was making is even the DSM set up tests to try and show consistency in psychiatrists for making diagnoses. And some of the indications, varies by indication, but some it is extremely heterogeneous what someone will diagnose with, the same patient.
Right.
Who's right? There's no biomarker. How do you know? It's opinion. It's subjective.
Mm-hmm.
There's no way to know who's right. And so that's a concern I have too. Whereas I think some of these RDoc-like deficits, or just let's say deficits in general, like I forget what you had said, but that is, I think, easier to measure and to target and understand than these global labels and diagnoses. Right. I just don't think they've been helpful.
But it's kind of a blessing to have the psychedelics all hitting the 5-HT2A. I mean, it's funny because it's a simplification, and we think, oh, the 5-HT2A is the answer, and then you realize that at a single molecule level, there's actually many scenario possible. So
yeah, and certainly all the serotonergic classical psychedelics too. I'll also, what's interesting is the NMDA receptor antagonists also show a lot of promise, and are the only approved, if you want to consider. I don't quite consider them psychedelics, but many people do.
Or
and then entactogens, right, as well.
Mm-hmm.
Yeah. And there is probably 2A involved, but downstream a little bit.
What are your thoughts on dimerization of the 5-HT2A with glutamate, mGlu2, mGlu3, and is there any relationship? Is there any role in biased agonism?
Yeah, it's a very interesting question. I'd like to see more work done on GPCR dimerization. I think there's a lot of complexities in sort of doing it and knowing exactly what you're measuring, but there are better and better techniques available. I don't quite know, with respect to the dimerization with the metabotropic glutamate receptors. I do think there's some interesting stuff there, and it would be neat, definitely, to test some of these bias compounds to see if they differentially respond.
And what are your current questions or research, if you can share a little bit about your upcoming projects or the projects you're working on? Are you still collaborating with Compass Pathways, for example, or
not currently? No, we're not doing the Discovery Center at the moment. So yeah, a lot of different things, right? Of course, crazy scientists do. But definitely a lot of 2A receptor work. I'm trying to think there what we're trying to do. I mean, I'm very interested in improving selectivity further. John McCorvey, a friend and collaborator of mine, always points out in his talks, like, we need better tool compounds. And so he's done some really cool work there. And I'm also very interested in, can we sort of improve the selectivity profile for 2A even more over 2C and 2B, and sort of use those to figure out maybe what role 2C may play in the psychedelic effects, because all psychedelics are 2C agonists, right? And even some of our bias compounds, although there's some selectivity over 2C, like that is a limitation. Like, there is some 2C agonism, right? And what does that do? We don't know. There's ideas, but having really selective 2A agonists has always been something the field's been trying to achieve, and there's been incremental improvements, but anything over like 10-fold, 5-fold has been really difficult. People have been working for decades. David Nichols spent decades on that, and it's really challenging. 2B, we've had more success with functional selectivity, so we can get 2B antagonism really easily now with these N-benzyls, and that's great because it's associated with the cardiac risk. It may have some psychoactive effects for some compounds. That's not clear. Different people have different thoughts. Also an interesting question. The other one we're really interested in is the serotonin 1A receptor and what potential role it may play with certain psychedelics. There's a lot of interaction between 1A and 2A at the neuron level, as well as behaviorally. A good example is 1A agonists will suppress the head twitch response. And many psychedelics, especially tryptamines and lysergamides like LSD, hit 2A and 1A fairly potently, but not all. Some don't really interact with 1A probably at any physiologically relevant level when they're taken at psychedelic doses.
In acute, I can see why the 1A would block the head twitch, the 2A induced head twitch, but in chronic, maybe that's not the case because of the desensitization of the 1A, maybe, I don't know.
Yeah, I don't know that that's been looked at. It's certainly an interesting question. And again, like, what that means to humans is unclear. Some people think maybe 1A attenuates the visual effects. Some of these potent 1A agonists are still very psychedelic. LSD, although LSD is still a bit 2A skewed, at least is what we're finding. But LSM 775, for example, is absolutely psychedelic. 5-MeO-DMT is another kind of classic example that has fairly high 1A agonism.
5-MeO, yeah.
So, it's a very interesting question. So we want to understand that. We also want to try to understand at the receptor level, why is it that the phenethylamines are not binding well at 1A? Because they don't really bind at all. There's a few interesting exceptions, but they show 100 or 1,000-fold selectivity preference for 2A over 1A. And so if you look at the binding sites, they're quite similar. There's obviously some notable differences that are important, but we want to understand why is that at the molecular level, and then see if we can use that to figure out the role of these different residues in binding potency as well as functional activity. Like, why is this compound an agonist?
You're right. When you look at psychedelics, the only psychedelic that has a strong 1A affinity on top of the 2A is the 5-MeO-DMT, and there's no hallucinations with 5-MeO.
Yeah,
if I'm correct.
It's kind of the classic example that's made people think that hypothesis.
Right.
But unfortunately, there's not. That one is like one of the more potent that has been tested by humans. There's another really interesting compound called 5-MeO-PRT. It's a pyrrolidine ring on the nitrogen. And that there's reports in TCAL, Sasha and Ann Shulgin's work, where that compound causes people to black out and have no memory in some cases, to feel really disoriented and intoxicated, to become nauseous. Again, it's of the classic tryptamines, it's, as far as we can tell, the most 1A selective. So but we don't know. I mean, again, it could be another serotonin receptor or another class A GPCR or whatever mediating those effects.
Mhm.
But because you brought that up with 5-MeO-DMT, like I think what's interesting and has always interested me about this question is some of the more bizarre tryptamines, like 5-MeO-DMT and 5-MeO-PRT, have this high 1A activity. So it's potentially indicating something unique about them. Whether it's 1A or not, I don't know.
Mm-hmm, mm-hmm. And where do you see, neuroplastogens activating, biased agonists activating 2A selectively, just to have only the therapeutic effects and not the hallucinations? Do you see that happening in the next 5 years?
So I think in many of the psychiatric disorders where psychedelics seem to work really well, I don't know. My personal opinion, I've had these experiences, is that the experience is core to the improvement. Now, that might work in synergy, additive with some physiological changes. I do think there's something physiologically going on, right? People describe this afterglow, but a lot of the behavior changes, the perspective changes, you talk to patients, if you've had these experiences, it's very clear that there's like deep-seated insights and revelations and understandings that you had during that experience.
Mm-hmm.
I have a hard time dismissing that as not therapeutically relevant to
Mm-hmm.
the improvements, especially when people clearly tie the improvements to insights they had often.
Mm-hmm.
I don't know if our current assessments get at that. Like, it's like trying to correlate the mystical experience with improvement, but maybe it's just cognitive insights about why am I doing this? Why am I arguing with my significant other? Like you sort of step back and sort of critically can look at yourself objectively and say, I shouldn't do that. And then when that comes up again, well, I had this insight, I'm going to change my behavior. Or why am I always so anxious? You see yourself, anxious and maybe projecting here, workaholic, doing all these things like what, I should stop and smell the roses, and so like I just, yeah, so I do think that, but I also believe there's some physiological effect probably working in synergy with the psychological effects, right? They're not mutually exclusive, and maybe they're the same thing at some level, right?
Mm-hmm.
We don't know. But to your question, do I think the really weak partial agonists where there's no acute psychoactive effects will work well in treatment-resistant depression or major depressive disorder? It's hard to say. I would be cautious there if it were my efforts and time. I think it's such an interesting question, but I think it's definitely a more risky development strategy from a drug development standpoint.
Mm-hmm.
But if you could do it, it's big payoff, because I think there's a lot of people that would be the kind of type of molecule they would want. Now for
Mm-hmm.
other disease indications and
Yeah,
disorders,
now that
who
we see that
knows? Yeah.
psychedelics can heal other indications that are not meaning
Yeah.
making dependent, like
Right, a cluster headache,
neurodegeneration,
right? Like there's no
Parkinson.
insight there. Yeah, Parkinson. There's so many other inflammatory disorders. Chuck Nichols has done a lot of really cool work on the anti-inflammatory effect of, not all of them do it, interestingly, but some of these compounds. So,
That's right.
I mean, yeah, I think like that's what excites me, is like all the other potential applications, and for our bias compounds, right? Like even it's not just like, oh, what could psychedelics do, but what could inverse agonists or antagonists do, right? Now we have these compounds that can somewhat behave like an inverse, but not quite. They do something different.
Mm.
They downregulate the receptor instead of upregulating it. Well, that might be
Mm.
really useful for psychosis or all sorts of disorders, sleep disorders that 2A antagonist, inverse agonists we know are efficacious in. There's human data for
Mm.
years,
Mm.
so that's really exciting too.
That would be interesting to look at 5-HT2A basal activity in schizophrenic patients, for example.
Yep. Yeah. And
Yeah.
pimavanserin and Parkinson's psychosis, like, yeah,
Mm-hmm.
there's a lot of potential there, I think, for clinical improvement with these biased compounds,
Mm-hmm.
because
Mm-hmm.
fundamentally they're physiologically differentiated. No one's ever tested it, as far as we know, anything like that. Like it behaves like an antagonist in blocking the G protein pathway, which seems to have the therapeutic effect, but not in the arrestin pathway.
Well, Jason, thank you so much for your time and your insights. It's you know, we could continue talk about this fascinating subject. I really believe this is I mean that phase in neuroscience is fascinating and groundbreaking. So thank you for explaining, sharing your insights, and stay with me. I'm just gonna say goodbye here to you. Thanks for tuning in. If you have any questions, please DM me, and I'll be happy to forward them to Jason. And our next guest will be Dr. Rachel Yehuda to talk about MDMA and PTSD. And thank you. And until next time, take care.